Hello again. In this video, we'll be defining the natural numbers. They're a key structure for discrete mathematics and really important throughout computer science. We'll see a couple of new concepts as we go, in particular recursion. So this is a video where it may pay to rewatch and it will definitely pay to read the text super closely. I'm going to follow this video up with a whiteboard video showing me evaluating some terms and sort of thinking clearly about the naturals, and hopefully that'll be useful for you. But I think that this is a really key thing, and it's really important to make sure that you get it. Okay, let's get started. So to start with, we're going to do these definitions inside of what's called a module. Modules are really common, just they're programming units, right? Most languages have some notion of module. We're going to use them to sort of give our own definitions and then say, hey, just kidding. We're going to use actually the standard ones in Coq standard library. So while it is true that Coq defines everything sort of from scratch, we're actually not going to work from scratch. We're going to use some definitions other people already gave. I'm going to sort of walk you through those definitions here, even though we're going to end up using theirs and not our own. Hopefully not confusing. So this starts a module called Nat Playground, and it's going to sort of hide some of our definitions from the broader world, so it lets us play for a minute. We'll do this throughout the course to sort of define little playgrounds like this. Okay, let's talk about numbers. You've probably heard of them. Numbers, familiar concept. Certainly, hopefully, if not, get in touch. So we're going to talk in particular about the natural numbers. So those of you who are into sort of pure mathy stuff might think like, what is that zero doing there? Who do you think you are, young man? And I'm just going to say that, well, computer scientists start at zero, and zero is a natural number for us. If you are taking a math class at the same time, I'm really sorry that mathematicians often disagree and say that one is the first natural number. And I think that that is just going to be really hard to keep track of. And I'm sorry. But this is how we do it. So zero is the first natural number. Um, uh, Whatever program you've done before, numbers probably already existed. There was some int type. If you were in JavaScript, integers and floating point, like decimal numbers, were just the same type. In Python, they're treated differently. In C, they're treated differently. It really varies how these types get treated. In Coq, we're building everything from scratch. We're going to build the numbers ourselves. We're going to do it in kind of a crazy way, and we'll look later on in the course at other ways of building them. We're going to build what are called the unary numbers. So the numbers you and I know well are the decimal numbers. That's base 10. And the numbers computers know really well, okay, those are the binary numbers. That's base 2. The numbers Coq knows really well are unary numbers. The metaphor I like to use here is sort of scratches on a prison wall. Hopefully that's not sort of like too real for your quarantine times at home, where you're like counting the days. The idea is they're tick marks, right? It's base 1 in that like there's only ones place and there's arbitrarily many of them. So to write the number 0, you would have no ticks. Here's the number 1, 2, 3, 4. That's 4 ticks. And then like if you're doing tally marks, then the fifth one would be a slash through or whatever. Right? This is the kind of number that the unary number is. Here is that definition in Coq. So we're going to have define a type nat, that's short for natural, with two constructors. O stands for 0 because you can't define a numerical thing. You can't use a digit as a constructor name. Z would have also been good. And then S is short for successor or suck, S-U-C-C. So this is 0, and this is successor. Right? And then as we've already seen, nats are a compound type. So successor says, hey, you tell me the number you're the successor of. So let's summarize what this statement inductive nat says. Okay, here's how how expressions in the type nat can be built. 0 and S are the two constructors. 0, O, is just a thing in the set nat. If n is an expression belonging to the set nat, then S of n is also an expression belonging to the set nat. Right? S applied to some nat gives us the successor of that. And then lastly, this sort of caveat says, hey, this is the only way. There's never going to be another way to build one of these. Right? We can write functions that use 0 and S, that use O and S in interesting ways, but these are all of them. Right. One thing worth remarking on, we just chose these names. I already remarked, oh, Z would have been good too. We could have gone with something more informative, and there's really something to be said for this. We could have said stop, says like, okay, stop counting, and tick says, okay, here's the number of ticks that I have. And we wrote n, because n is short for natural, right? It's nice to have variables that match up with various concepts. But like, kind of whatevs, right? We could have called it foo. Now, foo is a bad name. Foo is a name that programmers choose when they can't think of another name. Foo, bar, baz, cucks, right? These are names that came out of sort of the MIT AI lab culture in the 70s, I think, maybe a little earlier. I'm not sure what the exact history is. Um, some of it comes, I think, from military slang FUBAR, which you should look up, but maybe not if you have Safe Search on. Um, uh, with that fun historical aside, this is like another way to write it. This is what I would call isomorphic or equivalent to the other definition of nat, and it's also perfectly good. We're going to go with the other one though, right? That's just what we're going to use. These conventions are critical for any kind of formal work. You just have to pick something. Okay, let's define a function. Here's a function, pred, short for predecessor. Okay, Coq accepts the function. It's a good function. Let's think about what it does. Uh, you give it a natural number n, it's going to return another natural number. And if it's the successor of some n prime, we'll just return that n prime. So that's great. So if we ran compute pred s of o, we'll get s of o. Okay, well, think about it. This s of o, two successors, this is like, really, it's pred 2. And then what we're getting back out as the answer is 1. Okay, that makes sense. What about pred o? Well, it just says 0. So it's saying the predecessor of 0 is 0. Now, you'll probably see that and think, well, that's dumb. The predecessor of 0, the number that comes before 0, is -1. This guy does not know what he's talking about. And I would say no, you're right. In the integers, the number that comes before 0 is -1. 100%. I'm familiar with the concept. I've used it before. But in the natural numbers, there is no number that comes before 0. So we're just going to say by convention that pred truncates or saturates. When you take predecessor of 0, we're just going to say, it's still 0. You can't go any lower than that. This is, again, a convention. It's kind of an unfortunate property. Some of this comes out of a fact that we'll see more on a bit, which is that Coq requires that all of your functions be total. They have to be defined on every possible input. So that means we need to give we need to specify some predecessor for 0. We could have picked something else. Like we could have picked return 47, chirp chirp, Pomona Pride, but that seems like a crazy choice. Right? Like people are not going to be ready for that. And then you compute predecessor of a number, and it's like, oh, well, if the answer is 47, the number that you did predecessor of is either 0 or 48. That's weirder than saying, okay, look, if the predecessor for a number is 0, then your number originally was either 1 or 0. That seems a little more sensible, but we are going to have to watch out. We're going to have to be careful and pay attention to this. Okay. Cool. It turns out that Coq knows about Arabic numerals or Hindi numerals, depending on how historical you want to be here. You can write s of s of s of s of o, right, with the appropriate parentheses, and that'll compute the number 4, right? There's 4 successors. But if you ask Coq to print it out, it'll say 4, like a sane person. And that, to me, that's great news. Like, what wonderful stuff. Like, Coq can speak this language. And that's just a thing that Coq knows about. It's just sort of built in. So we could also say check 4, and it says, oh yeah, 4 is a nat. What about, 47? Yeah, absolutely. What's pred 47? 46. Okay, great. This is hopefully a relief to you. At core, Coq is working with these S's and O's. Fine. But you can enter numbers and Coq knows what you're talking about. That, I think, is really nice. Okay, let's define another function. Here's the saturating or truncating -2 functions. This is like 2 predecessors. It should compute 2 less than a number. So you give me a number n, and then let's look at this last case first, because it's the one that does the right thing. Successor of something. Okay, interesting. We've done a compound pattern here where we're matching 2 successors. And then we return the inner thing. This is like stripping off 2 layers of successor. Nice. So this will give us the number 2 less than the one we had in our representation. Now, if the number is 1, s of 0, there's no number 2 less than 1 in the natural, so we'll just return 0. And it's the same story for 0. If you've already given me 0, I can't go any lower. Right? This is as low as it goes. We've hit rock bottom. We'll return 0. But for numbers greater than 1, we'll get the right answer. -2, 4 gives you 2. -2, 27 gives you 25. Okay. This is probably a little weird, but hopefully it's also a little cool. Like, we just defined numbers ourselves. That's pretty wild. Okay, quick quiz. We're going to do these quizzes sort of throughout the class. This is not for a grade. This is for checking your understanding. How would you write the number 4 using our representation of nats? I'll give you a hint. We've actually already seen it. Um, the thing to do when I do one of these quizzes is pause the video, write your answer down, think about it for as long as you want, and then I'll tell you the answer. You unpause the video, you'll see what it is. Okay, so I've sort of built in a pause by dissembling right there. The way you want to write it is like this. Right, first we can check that it's a nat, and it says, oh, 4 is a nat. Right, if you like, we could change that to a compute, and we'll get actually the exact same answer with an equal sign at the front. So this is how you do it. To write the representation of a number n, you just want n successors on 0, and you need to wrap parentheses, right? If we asked it to do something like this, we'll get an error message saying like, hey, S is of type nat arrow nat. It's a constructor that's waiting for a nat, and you just gave it to this nat, because remember, this is how Coq sees this. Because application is left associative. So it's really important, right? This is how Coq sees the thing without any parentheses. So it's really important that you write the parentheses to make it right associative, to sort of right apply things. Okay, almost done with numbers. I want to introduce one more concept here: recursive functions. So a recursive function is the way in functional programming that you get a loop. There's no loop construct in Coq. No for loops, no while loops. You're going to do it all this way. So the way you define a recursive function is with the word fixed point. So fixed point says, hey, I'm defining a name. Fixed point is like definition, except for you're allowed to use the name in the body of its definition so long as you call it on something smaller, something structurally smaller. And we'll talk about what that means. So here's a definition of even b. You'll notice we have this convention where the b in the name of a function lets us know that it's going to return a boolean, neg b, and b, whatever. Here, even b is going to take a nat and return a bool, and it's going to tell us whether or not a number is even. Let's look at how it works. Okay, so it looks at n. That's really all it can do. Match is sort of the only game in town. We'll look at the cases top down. If it's 0, if n is the constructor O, well then wait, O represents 0, and 0 is an even number. Return true. Beautiful. This is a base case, right? It's sort of one of the low entries in the data structure we're talking about, the naturals. If the number is S of O, that is to say 1, return false. 1, I believe, is an odd number. Okay, otherwise, if it's not 0 and it's not 1, we must be successor of some other number. In that case, okay, look at that other number, n prime. Well, if we strip off 2 layers, if we strip off 2 numbers, well, that's going to be the same parity, the same even oddness as the greater number, right? If 4 is even because 2 is even because 0 is even. So what we'll do is we'll make a recursive call to say, okay, find out if this smaller thing is even. One thing I want to note, so this definition is accepted. What would happen if we forgot S of O? Coq would say, non-exhaustive pattern matching, no clause found for pattern 1, which is, okay, pattern 1, that's the S of O we've got right here. Okay, cool. So Coq has really got our back here. Let's play with it. Compute even b 6. True. Beautiful. 8. Good. But okay, let's check an odd one. Great. Okay, let's give it a real challenge, huh? Beautiful. Okay, one other thing I want to know, after we define it in the response, we get a little remark, even b is recursively defined. It's like, oh, yeah, that's right. We said fixed point. We want it to be recursively defined. And then it says decreasing on first argument. Okay, that's a little funny. There's only one argument, n. But what it's pointing out is saying, look, I accepted this recursive definition because every recursive definition needs to be defined in terms of something smaller. But this n prime is smaller than the s of n prime that came in on this recursive call. So I'll accept it. This is something that's clearly smaller, and this is okay by me. If you don't call on something smaller, Coq will reject your program. We've got some discussion of that later on. Okay. We could define odd b by a similar fixed point, but we could also just say, well, the odds are the things that aren't even. So let's just cut out the middleman, keep it simple. Right, so here's a perfectly good non-recursive definition. Pros and cons to defining things recursively or not. I think it's fine to define it either way. Before we move on to the next bit, I want to make one other remark, which is that we can use these Arabic numerals here. And if we wanted to, we could write this, and this is also a perfectly good definition. I think it's a little nicer to use the constructors because it'll keep you honest and keep things a little clearer for you. But I want you to know that that's available. Okay, let's keep going. Here's another function, this time multi-argument. We're going to define addition. So let's look at how it works. Plus takes two naturals, n and m. It was pointed out on Zulip that I could have also written this. This is totally equivalent. It's just a way of saying, hey, I take two arguments, n and m, both of type nat. And here I take an argument of type nat and another argument of type nat. Same deal. Okay, what's the idea here? What we're going to do is we need to add these two numbers together. So the number of successors in n and the number of successors in m, well, we want to add those two, and that'll be the number of successors in our returned thing, the value we return. So the way we're going to do it is we'll look at n, and we'll say, hey, if n is 0, 0 plus anything is just that other thing. So just return the other number. Otherwise, if n is the successor of some number, then take the successor of the recursive call on whatever's left of n. You can think of this process as sort of transferring successors from n to m, and that's mostly correct except for nothing is getting changed here. We're returning a new number. Okay, let's check our work. Mini quiz, what do you think plus 3, 2 should return? I'm fingers crossed for 5. Let's see what happens. Beautiful. Let's see how that works. So there's a little bit of a run here that it shows how it steps. And again, we're using this substitution model of function evaluation. So to compute plus blah, 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 we'll get this. And then we're just saying, oh, by the second clause of the match, we're going to be in this case over here, where this is our n, which means that this is our n prime. So we'll do s of plus, and then here's our n prime. And then you'll notice m actually stays the same the whole time. Okay, and then this derivation sort of goes through, showing how all this steps down, and then we get something with 5 successors, having moved the 3 successors here onto what was left of m. Okay, here's multiplication, which we're going to define in terms of addition, which is how you did it maybe in like first grade or whenever you learned about multiplication. N times m is m plus n minus 1 times m, right? Multiplication is just iterated addition. So here's us doing that. To do n times m, well, if n is 0, we return 0. 0 times anything is just 0. If n is the successor of anything, well, then we need at least one more m into the result of recursively multiplying. So let's check our work. These little test cases are critical checks of understanding. Mult 3, 3, this should be 9. Beautiful. Mult 5, 2. What do you think, 10? Feeling good. Okay, I think this is the last one for this video. Minus. So here we're going to define minus as iterated subtraction. We're going to do it in a special way. So this is yet a new form for how matches work. We're going to match. So here I've used the double argument notation. Here we're going to match on two things at once. We use the comma notation there. How does it work? So this is basically saying, hey, I want to simultaneously consider the possible ways that n and m were constructed. And let me tell you what the possibilities are. To compute n minus m, if n is 0, we need to saturate. You can't go lower than 0. So if n is 0, I don't care what m is, return 0. If, on the other hand, m is 0, okay, to get to this line of the match, we know n can't be 0 because we dealt with that case right here for all m. So that means n is the successor of something. Okay, in that case, if we're subtracting 0 from something, just return our original thing. We could have also written this. Right? Rather than doing that, we wrote underscore there and said, hey, please just return my original n. So you're allowed to use a name here more than once, and matching on something doesn't make the other thing go away. Okay, lastly, maybe it's the case that you have successors on both n and m. Okay, what we'll do then is iterated predecessor on both. So to compute, n minus m, we'll say, well, look, if they're both successors of something, then just take one away from both. And we'll work our way down. Eventually, one of them will hit 0, and then we'll know what the minus is. Okay, so this is saturating, just like pred, but let's check it. Minus 2, 2, 0. Great. Minus 2, 1. 1. Minus 10, 3. 7. Looks like it's working. Let's check the saturation. Minus 3, 10. 0. Okay, great. If this is surprising to you for any of these, what I recommend is take out a sheet of paper and just carefully work through the substitution model of how minus works here. So I'll have a whole video dedicated to that coming up next, but you should hopefully have seen just from the text here so far how the general idea works. Okay, so that's minus. So here's exponent. Just one last thing to look at. I'm not going to remark on it here. Uh, you have an exercise where we ask you to define factorial. We give it to you in math notation. You'll need to translate that math notation. And then lastly, okay, just like we saw for the booleans with and or, we can define the usual operations with the correct order of operations. So 0 plus 1 plus 1, compute 2. If I write it 2 times 3 plus 4, okay, these are like these things that go around, right? Is this 6 plus 4 is 10, or is it 2 times 7, 14? Well, PEMDAS or whatever says that it should be 2 times 3 plus 4, 10. Okay, beautiful. So these notations let us use the familiar notations. I'm going to conclude this section by remarking on what we just achieved by defining these notations. In the span of about 15, 20 minutes, we define numbers, defined operations on them, and now we're writing arithmetic expressions that seem to certainly behave like the way we expect them to. To me, this is absolutely remarkable. We are building our own world as we speak. Okay, got a couple more videos coming up next. The one I hope to make next will be about this substitution model of evaluation. I'll do a bunch of examples on the whiteboard, and then there's a couple more videos just about defining other functions in interesting ways. Okay, talk to you soon.